Welcome to this lecture. This is the second lecture of week 1. I am sure you have already gone through the introductory lecture video. I have already described the mode of conduct of lectures, which will be through some pre-prepared slides. I will be describing and discussing the materials that are already written on the slides. Let us start. In the first introduction, we have recalled the notion of random experiment, which can be repeated as many times as we need and observe the outcomes of certain specific random phenomena. And if we list all outcomes, if we list them in a set, we get the sample space. We also observed that special subsets appear as events, and these events satisfy certain algebraic properties. For example, if you take an event and look at its complement, so that is nothing but the complement of the set in the sample space. So the complemented set can be interpreted as the non-occurrence of the original event. So the complementary event can be given some physical significance, and these are the type of interpretation that we want to do. So this can be more formally done when we discuss the collection of all events related to a specific random experiment. These collections of all events satisfy certain specific algebraic properties like complementations and unions. In this lecture, we study these algebraic properties and model this collection of all events related to a specific random experiment as a sigma field. These terms sigma fields shall be discussed and defined in a minute. In this regard, note that the sample space by construction is a non-empty set. So whenever you perform a random experiment, you always get an outcome. So therefore, the list of all outcomes is a non-empty set. So more generally, to discuss this mathematical foundation behind the study of probability, what we shall do, we shall work with the notion of sigma fields in quite a general setup, and we shall work with a non-empty set which shall always be denoted by omega. So in this course, if you find this omega notation, you always treat it as a non-empty set. In reference to a specific random experiment, this omega is to be taken as the sample space. Okay, so in general we shall work with some non-empty set. So let's start discussion on the definition. What we shall do, we'll start off with this non-empty set omega and look at collections of subsets of omega. Okay, so this script f denotes some collection of subsets. What we want is that this collection of subsets should satisfy certain properties. So the first thing is that the empty set, which is a subset, a very specific subset, should be in the list. And this is what we write in mathematical notation, that the empty set belongs to the list, belongs to this sigma field, belongs to this script f. Okay, so this is the notation we write. So here a set is actually an element in the collection. Alright, so that's why we use this notation. So the second property that we want is closure under complementation. What do I mean? So for all possible sets in the list, so the list need not contain all possible subsets, but whatever subsets they are there, if A is there, then we should have the complement also in the list. Okay, so this is what we mean by closed under complementation. Okay, and the final property that we want is closure under countable union. What do we want? So we will take sequences from the list. So A1, A2 and so on are subsets. These could be repeated or this could be distinct, but a priori this arbitrary collection, this arbitrary sequence of sets A1, A2 and so on, they are taken from the list, from the collection, and then we want to look at its union. So since we are looking at a sequence, I get n from 1 to infinity union an. This set, this union is a subset, and I want this union to be also in the list. So if some specific collection of subsets, script f, satisfies these three properties. Empty set belongs to the list, closed under complementation and closed under countable unions, I shall say that this collection is a sigma field. Okay. Alright. Now there is an equivalent term which is called a sigma algebra. Throughout the course we shall use the term sigma field, but sigma algebra is an equivalent terminology. Alright. Before going into examples, what we do is that we study some very basic properties which shall help us in construction of examples. So let's start with some basic properties. So let script f be a sigma field of subsets of a non-empty set omega. Then the following statements hold. Alright. So the first statement says that the omega must be in the list. So how do you show this? I have given a hint. So use properties A and B given in the definition. So let's go up. So if you look at the first property A, then it says that the empty set is in the list. Empty set belongs to the element, belongs to the sigma field. Then the second property says that closure under complementation. So if you now look at complement of the empty set, which is in the sigma field, then the complement of empty set should be there, but the complement of the empty set is nothing but the whole set, so therefore the whole set is there. So this proves the first property. Please try to write this down. Alright, so let's look at the second property. This says closed under finite unions. So what do I mean? I take finitely many sets a1, a2, an from the sigma field, and what I want is that the union should be in the sigma field. So the union here is a finite union of sets. Alright, but in the statement, in the definition, what we have taken is a countable union. So how do you put it in that framework? So what do? We take this sequence a1, a2, an as given sets, and then from the n plus 1th place onwards you repeat the empty set. Remember, empty set is always there in the sigma field. So therefore this sequence that you have just constructed, just looked at, this sequence is a sequence of sets coming from the list. Okay, these are not arbitrary subsets, these are not arbitrary subsets of omega, but these are arbitrary subsets from the list. So this is very important. So I have taken a sequence from the list, from the collection. Then if you look at this union is nothing but the finite union I from 1 to n of ai's. Alright. So therefore, since this countable union collapses to this finite union must be in the collection script f. So this shows closure under finite unions. Similarly, using properties involving countable intersections and finite intersections can be shown, where what you want to show for countable intersections is that if you take a sequence of sets in the sigma field, then their countable intersection is also in the sigma field, and you can also reduce it to finitely many intersections. If you take finitely many sets, take their intersection, then that should also be in the sigma field. So to prove property Roman 3 and Roman 4, all you have to do is to use some algebraic properties involving complementation and union. Please write this down, and I have left this as an exercise. These are very easy exercises and it will help you understand the material better. Okay, so now we have some idea about the basic properties and we are ready to construct examples. As per the discussion above, any sigma field must contain the sets empty set and the whole set, right? So this we have already seen. It so happens that if you look at this collection of two sets, only the empty set and the whole set, so this is now a collection, this becomes our first example of a sigma field. So please check that the empty set is there. Then if you look at complements of each set in this collection, empty set's complement is whole set omega, omega's complement is the empty set. So therefore this it's also closed under complementation. Now if you take sequences out of this, so either empty set or the whole set will be there in the sequence. It could also be repeated, so they could be also be mixed. In whatever situation, if it so happens that only the empty set appears in the sequence, then the union is empty set. Otherwise, if omega appears at least once, then the union becomes omega itself. So therefore it's also closed under countable unions. So both these properties are true. So therefore this simple example gives us the first example of a sigma field. This is sometimes referred to as a trivial sigma field. On the other extent of the things, we can look at all possible subsets, which is called the power set. So this is the set of all subsets of the non-empty set omega. So this is sometimes denoted as 2 to the power omega to denote that each element in the omega can have two choices, either you take it or not take it. In this sense, you get all possible subsets. Okay, so this is the idea. So now if you look at the power set, so this has the list of all possible subsets of omega. Now this will become a sigma field, because no matter what kind of set operations you perform, you always end up with a subset of omega, and therefore it's always closed under all those complementation as well as countable unions. Okay, and also the empty set is a subset, so it should also be there. Alright, so therefore the power set becomes a example of a sigma field. Now we have two examples of sigma fields. One is the trivial sigma field, other one is the power set. What we are interested in are arbitrary sigma fields which falls between these two things. So arbitrary sigma field will always contain the empty set and the whole set, so therefore this inclusion is fine. On the other hand, arbitrary sigma field is nothing but a collection of subsets, so all subsets are there in the power set, so therefore a sigma field is actually a sub collection. So that's why I have used this as contains notation. So sigma field script f is a sub collection of 2 to the power omega, the power set. We are going to see examples of script f which is strictly between these two things. Specifically, if you are going to work with finite sets or countably infinite sets, then instead of using arbitrary sigma fields, we typically work with the power set. Okay, so for example, if you are working with the example of coin toss, you get the outcomes h and t, heads or tails, then the sample space is made up of these two elements, so omega is this set. Then you look for all possible subsets of omega, so that is the empty set, two singleton sets h and t, and then the whole set omega. This gives you a list of all subsets of omega, which is the power set, and as per our discussion above, this gives you an explicit example of a sigma field on omega. If omega is an uncountable set, if it has more elements, then what will happen that for technical reasons we do not use the power set. It will happen that the power set has too many sets to handle, and in principle we are not going to work with all possible such sets. In case of such sets, for example interval 0 to infinity or the real line, it will have too many elements, too many sets. So what we shall work with are specific sigma fields in these situations. We shall discuss this issue later on. One specific terminology is useful. We shall say script f is a sigma field on omega instead of saying script f is a sigma field of subsets of omega. Instead of saying this whole thing, we shall only say script f is a sigma field on omega. Alright, now let us look at further examples of sigma fields. We are interested in examples which exactly fall between the trivial one and the whole power set, right? To construct these examples, we first take a bottom-up approach. So what is this bottom-up approach? What we do, we look at the trivial sigma field and add sets to this. So take some non-trivial subset capital A, which is not the empty set and also not the whole set. Okay, so I take a non-empty set omega and take a non-trivial set capital A. Then look at this collection of sets: empty set, the set A, its complement, and omega. You can now try to check, does this set of 4 elements construct a example of a sigma field. So all you have to verify is that empty set is there, which is also already seen. Then you have to check that complements of each set is there, and then you have to check that if you create sequences out of these 4 elements, then you always get closure under that. Okay, so please check this. So this will become an example of a sigma field which is slightly more general than the trivial sigma field or the power set. Alright, so now you can ask, okay, so I had taken one subset, what will happen if I take two proper subsets? So to do this, let's see what happens. So take two proper subsets A and B. So therefore A, B are two subsets usually distinct, such that they are not the empty set and also not the whole set. Then it will end up with 16 possible sets. Okay, so I have listed them. So it will of course have A, B, empty sets, A, B, then A complements, B complements, and then you shall see all this union and intersection operations appearing here. And you also see combinations of complementations and so on. In particular, I wish to draw your attention to this set, which is called the symmetric difference of two sets. What is this? This is this notation. So I write a big triangle B. This thing denotes the symmetric difference. So A symmetric difference B is exactly the set consisting of elements which fall in exactly one of them. So they are not in the intersection between A and B. So either it's in A, not in B, or the elements should be from B but not in A. So list of all such elements of omega will construct you the symmetric difference between the sets A and B. So this symmetric difference will appear in the sigma field, and its complement is also going to appear. Here I wish also to draw your attention to this notation that A intersection B complement can sometimes be written using this set minus notation. I shall only write A minus B to denote all elements in A which are not in B. So as if I am subtracting out all elements of B that appear in A. I am subtracting them out. So that is this notation. Okay. So in this list you will shall have at max, at the most, 16 possible sets. But it may so happen that A intersection B is empty. So let's go up again. So in this list A intersection B appears. If it so happens that A and B, the two proper subsets that you have taken, they are disjoint, then A intersection B becomes empty set, so which is already listed. So in principle, when you are working with specific examples, this list of 16 elements or 16 sets may collapse and give you less number of sets. So this is the maximum possible thing that you might have. Okay. So in such cases, we shall get less number of sets in the collection that we have explicitly listed. More generally, what you can say is this: if you have n many sets a1, a2, an, then you shall have n distinct subsets of omega, and it can be proved that there are at the most 2 to the power 2 to the power n sets in the sigma field constructed using the above method. So what do I mean? So if you just go back to the example, here we had constructed first sigma field using only one set. We had 4 sets, so that is 2 to the power 2 to the power 1, 4 sets. Then you had taken 2 sets. Then here you as per the statement there, you are expected to have 2 to the power 2 to the power 2, which is 2 to the power 4, 16 elements. Okay, 16 sets. So this is at the most, and as we have already explained, if you have some relations between the sets, the list of 2 to the power 2 to the power n sets may collapse and give you less number of sets at the end. So this will happen in specific examples. But you shall only have at the most 2 to the power 2 to the power n sets if you start off with n subsets. It can be shown, take it as a fact. Okay. In a later lecture, we shall discuss a top-down approach to construct non-trivial examples. In the above discussion, what we have done is that we have constructed examples using the bottom-up approach. We have started off with the trivial sigma field and then started adding sets. So from the bottom, we are going up and getting bigger and bigger examples of sigma fields. We now discuss the concept of pre-image of a set under a function. Here, take a function between two sets, domain omega and range on the range omega prime. Then if you take a specific subsets from the range side, let's call capital A to be a subset. This is an arbitrary subset. Then you can consider this following subset, which is denoted as f inverse of A, which are all elements in the domain such that f of omega falls in the given set capital A. So capital A is a specific subset on the range side, and f of omega should be in the range side, that specific subset. So I list all such points in the domain side. So this is called the pre-image of the set A under f. Here you need not have an inverse. The function f need not have an inverse. Thus, f inverse of a should be treated as one symbol and not created by separate symbols f inverse and a. So here the function f need not be a bijective function and need not have an inverse. Alright. So using this notation, you can now try to work out this exercise, which says that you can take a sigma field on the range side. So take this function, take a sigma field on the range side, then look at pre-images for all sets that are in the range side. So I take a sigma field on the range side, take all sets that are in that specific list on the range side, look at all its pre-images. So this is a kind of a list of all pre-images. This is the collection of all pre-images. Then what you can now try to look at are this list of all pre-images. Now try to show that this is constructing an example of a sigma field on the domain side. So the pre-images are specific subsets on the domain side, and what you are trying to do is to show that this constructs an example of a sigma field. Okay. We now discuss a concept very much related to a sigma field. So take a pair consisting of a non-empty set and a sigma field of subsets of this given set. Then if you look at this pair, this constructs a specific structure. This is what we define. We call it a measurable space. A pair omega comma script f, we write it in brackets like this, is called a measurable space if omega, the first thing in the notation, is a non-empty set and scripted f is a sigma field on omega. This is called a measurable space. So if omega is the set of all outcomes in a random experiment and script f is any sigma field, then the pair becomes a measurable space. So this is a more explicit example that you might get from a random experiment. More specifically, we discuss some examples here. We have already discussed that if you take a non-empty set omega, then the trivial sigma field is always there as an example. So if you write it down in this pair format, this gives you an example of a measurable space. So omega together with the trivial sigma field constructs you an example of a measurable space. Then if you look at omega together with the power set, this gives you another example of a measurable space. More explicitly, if you are working with the random experiment of tossing coins, then your sample space omega is made up of two elements, heads and tails, and then you can also look at the power set, the set of all subsets. This is an explicit example of a measurable space. Later on, we shall discuss this notation of sigma fields BR, which is a sigma field on the real line. We shall discuss it in a later lecture. This is kept there just for your understanding that on the real line we are going to discuss some specific examples, and recall that we have already mentioned that in this uncountable set situation we are going to look at specific subsets. This shall be discussed in a later lecture. One final comment before we stop is that given a measurable space, we refer to the subsets that you have in the sigma field as measurable sets. So sigma field script f is on the non-empty set omega, and sigma field script f need not be containing all possible subsets, so it need not be the power set. It is listing some specific subsets, some special subsets. These subsets, given the sigma field, these special subsets, we shall refer to them as measurable sets. In relation to a random experiment, these measurable sets are exactly the events. Okay, so in particular, if you go up the occurrence of the single head or single tail, they are specific events in relation to the random experiment of tossing coins. Okay, so we stop here.